What's up, everybody? Welcome to lecture 15, which is over section 2.9. Now, section 2.9 is all about this idea of linear approximation, or linearizing a function to some extent. Now, what that means is that we're going to use the tangent line, or rather the line tangent to a function at a point, x equal to a, y equal to f of a. We're going to use that tangent line to approximate values of our function. And to give you an idea of what that's going to look like, let's consider this example here. We've got some function f of x, and we found its tangent line L of x. I'm just using L here because we're using it as a linear approximation. Now, what we're going to do is we're going to say, all right, cool, let's check out a couple of these points immediately around x equal to a. Let's go something like this. Around these points. If we look at those points, we'll notice that our tangent line is pretty damn close to our function. Pretty damn close. And for that reason, it's a really good approximation of our function. So if we wanted to find out what our function was for any of those points inside of that interval, we could just plug in those x values in that interval into our tangent line. That's it. That's the whole idea here. And the reason why is because, look at this. This difference is tiny. This difference is tiny. So it doesn't really make sense to go through the process of finding what our function value is at every one of those points, right? This linear approximation is really good. So for that reason, let's just use that. It's a lot easier to work with. Now to see what that's going to look like in practice, let's check out a particular example. So what we're going to do in this example is we're going to start with the function f of x is equal to square root of the quantity x plus 3. And then we're going to take and find the line tangent to it about a equal to 1. Or another way of saying that is x equal to 1, right? So what we've got is the tangent line in green and the function in purple. And we're going to use that tangent line to approximate the square root of 3.98 and the square root of 4.05. Now, how are we going to do that? Well, we're going to start by saying we need to rewrite everything in terms of f of x, just to find out what our x values are, right? So we want to know what 3.98 would be equal to, or rather, what x would be equal to, given that x plus 3 is equal to 3.98. This tells us that x is equal to 0.98. And the next step is to look at the square root of 4.05. And that tells us then that x is going to be equal to 1.05. All right, so what I'm saying here is if we want to approximate the square root of 3.98 using the linearization of the function square root of x plus 3, then we need to go about finding the tangent line, which we've already done. I've already written that out for us because we know how to do that. But then identifying what x value we need to use for our lower bound and what x value we need to use for our upper bound. And that's what this is doing. This is saying, all right, if you want to approximate the square root of 3.98 using the linearization of the square root of x plus 3, you need to know what x is. The only way to do that is by setting the square root of 3.98 equal to the square root of x plus 3, solving for x. Obviously, that's going to give us 0.98. And then to do the same thing for the square root of 4.05, we need to set that equal to the square root of x plus 3. And obviously, that's going to give us x is equal to 1.05. Now, we know what our boundaries are. We know what our interval of approximations are going to be, right? And I went ahead and drew it out on the board. We're approximating the square root of all values between 3.98 and 4.05. We're going to do that by coming over to our function, square root of x plus 3, finding its linearization, and finding the solution to its linearization between 0.98 and 1.05. That is to say, x equal to 0.98 and x equal to 0.5. My mistake. And x equal to 1.05. So now, all we're going to do is plug those numbers into our linearization. We're going to say that that is a good approximation for what the square root of 3.98 is. In other words, all of this tells us that L at 0.98 is approximately equal to the square root of 3.98. And coming down here, L at 1.05 is a good approximation to the square root of 4.05. And that's it. That's all this is. You're saying, all right, what is it I'm trying to approximate? How can I rewrite it as a function? Then, let's find the tangent line that's going to be appropriate. And using that tangent line and the values that we're trying to approximate, let's find out a good approximation for what we're looking for. That's it. Yeah, I don't have another way of saying that, I guess. Yeah. Having said that, let's keep chugging along. Now to wrap up this section, there's two things that I want to talk about really quick. First is the differential dy, and the second is the change in y, and what these things actually mean. So looking at the differential dy, what this is a way of measuring how much that tangent line is going to change relative to changes in x. In other words, since dy dx is equal to f prime of x, we have that dy is equal to f prime of x times dx. Okay, what? Well, what we're saying here is, let's say that our change in x is small enough that we could say it's approximately equal to dx. In fact, let's say that it's so small, might as well not even consider it an approximation. Let's just say the two things are equal. So we're going to hold dx and delta x to be equal. When we do that, we get that the differential dy is equal to f prime of x times dx. Or in other words, f prime of x times the change in x, delta x. Now, compare that to the change in y, delta y. We start off by just observing that from the slope formula, we have that the change in y divided by the change in x is equal to f evaluated at x plus delta x minus f evaluated at x, all of that divided by delta x. So because of this, if we were to multiply both sides by delta x, we would get that delta y is equal to f evaluated at x plus delta x minus f evaluated at x. Now there's a very important thing to note here about these two definitions. Delta x, we're saying, is equal to dx. But delta y is not equal to dy. Very, 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 very rarely do you get that delta y is equal to dy. Very rarely. Only for lines. That's it. Only for straight lines. Now, what is it this dy and this delta y are measuring? Well, the delta y is measuring the literal change in your function. That's what delta y is measuring. The actual change in your function. And that makes sense just looking at this, right? Now what dy is measuring is the change in your tangent line. That's it. That's all. It's measuring the change in your tangent line about that point. The end. That's all. So dy is measuring how good of an approximation that linearization is. At least when you compare it to delta y. So knowing about these two things is useful just by knowing how to compare, or to kind of consider the accuracy of that tangent line, right? Having said all of that, this idea of linearization, it shows up in computer science, it shows up in chemistry, biology, engineering, in numerical analysis, in all sorts of places like that. In the realm of engineering, it oftentimes shows up with approximating curves. So for example, AutoCAD, I suspect, I don't know this for an actual fact, but I very strongly suspect when it takes and creates your linear splines, your just straight line splines, to create that image of the circle, that what it's using is linearization. Certainly you could use it in programming to do just that. In fact, it would be a brilliant way of doing it because it reduces the math hugely for you, and the programming for that matter. Other places it'll show up is oftentimes when we start talking in higher level math courses about solving different solutions or finding different solutions, we start off by linearizing different problems. So this might show up in an AI class, in a data analytics course. Biology, again, this can show up in places like modeling for very short terms how a population might increase. Let's consider a COVID model, right? Chemistry, similar places, it could show up in rates of reaction. In fact, what is oftentimes taught in some of your early undergrad courses when talking about measuring the rate of reaction, that oftentimes is a linearization. Just because you're assuming a lot of information about the instantaneous reaction. So that's all I really have to say about linearization. Just know that there is a difference between the differential, the change, and a difference in the differential dy, and the change in y, delta y. They are not identical values. They have similar meanings, but they're measuring different quantities. And because they are measuring different quantities, we cannot say that delta y is equal to dy. However, we will always hold that dx is equal to delta x. And that for sufficiently small delta x's, the linearization of your function is sometimes adequate for approximation purposes. Excuse me. So having said all that, I will let y'all go. If y'all have any questions, by all means, feel free to shoot me an email. And do check out the notes. The notes, I think, that I wrote up do a little bit better job than what I may have just done here. Certainly there's more examples in them. And there's some more graphical information to better explain some of this. But yeah, have a good one, everybody. That's all I gotta say.